And we are now recording. All right, welcome everybody to part 2 of our deep read of The Location of Polar Aurora by R.J. Livesey. We have put the link to the article in the chat, and when this is online, I'll put it in the description as well. Liz, do you want to go on and summarize how far we got to?
Yeah, we got to the bottom of, or near, let's see, page 257. There's a table, and we got basically to that table. I could give a brief summary of the earlier parts of the article. Actually, for some of the folks who weren't here, maybe you already did listen to that, or maybe a summary would be helpful.
Let's
do
do
you want to mention that, Hannabella? I can do a summary anyway.
Let's do a last time on Aurorasaurus deep reads articles.
Okay, last time we started this article and we just each read a paragraph or so. If it's a short paragraph, maybe 2 paragraphs. And then we kind of talked about what it meant and sort of crowdsourced reading the paper. And, you know, kind of, I gave more interpretation, I think, of how to read it and what it means. But then we, you know, had good discussion of some of the technical terms, and we all kind of learned something in this way and made it maybe a little more approachable. This is an article that was written for the British Astronomical Association, which is a long-standing group, and it was written by one of their leaders, and it still has a lot of relevance today, and like, it's very well written in that each sentence really is succinct and means something, and so we can kind of parse through it. The first part of the paper goes through what the difference is between geographic coordinates and geomagnetic coordinates that are centered on the Earth's geomagnetic pole, and how that relates to the location of the aurora. So you can see that in geomagnetic coordinates in the first figure. You can see kind of the difference between the geomagnetic latitudes and geographic longitudes in the fourth figure, which is centered on the UK. Well, no, sorry, it's centered on Europe. And then there's a discussion of different types of aurora, how frequently aurora were observed by this group of scientists, which for, I think most of this paper is about like a lot of the 70s. They were very actively observing, and probably even farther back than that. And of course, similar to today, the solar cycle significantly changed how many events you would see, especially in the UK, in the north of the UK. Yeah, so we're getting into the second part of the article. I also did want to mention that I reached out to the British Astronomical Association and their current chair, and I just wanted to pass on that we really enjoyed this article and see if there was any way to contact the author today. And he is retired and not active in the field anymore, and he doesn't do email, but Sandra from the BAA did let him know that we really appreciated his article, and so I also do have an address if anyone wants to drop him a note. But he's written many very interesting articles and observed for decades. And so he observed not just aurora, but sunspots on a daily basis, and many other types of phenomena, astronomical and heliophysical phenomena. So that's really quite great to celebrate that as well. Okay, so I was going to start by talking a little bit about this table, where we're at, and then we can kind of go into the reading. Anybody else want to add anything to the summary or say anything? Ask any questions?
I think we're good. Thanks, Liz. So we're looking at a table right now that has columns that read location, suspected glow, glow arc, raid arc, ray storm, active movement or brightness, corona, and all sky storm. And they're looking at Lofoten, Shetland, Glasgow, and Cambridge for those. So if you turn to page 257, about 2/3 of the way down, you'll find this.
Yeah, thanks. And so the way this table is laid out, any kind of table or plot, you know, you're kind of really trying to ask, what am I trying to get from this? And what is the author trying to convey? And in this case, the table on the x-axis, the columns, sorry, are labeled with different types of aurora, and they range from you know, just a suspected glow all the way up to an all sky storm. And then the way the rows are laid out, they start from high latitude and they go to low latitude. And so one thing I was looking at this, I was just looking at this table and I was like, in this case, it's a distribution of the most active auroral form reported on a given night by any observer in the late 70s. And so they don't tell us too much more about exactly how they collected those stats. But for instance, you can see that the highest latitude, Lofoten, the most frequently observed type of aurora was the raid arc, followed by active movement or brightness. And so that is consistent with a lot of like substorm kind of behavior. And then going down to Shetland, the most frequently observed type of aurora there was a glow. And I also noted that they got a corona, which is very rare, you know, when all the aurora goes to a point in the sky. That was another type that was the latitude that most frequently saw a corona. So there's a bunch of different factors that go into how these frequencies come out. But then if you go down to Glasgow, the arc was the most frequent type. And if you go all the way down to Cambridge, in these stats, basically just a glow was 76% of those observations. And so one thing we don't know with just percentages is how many observations went into each bucket. But yeah, it's there's more to it than you could get, but I think that's a basic kind of thing. Is there anything that sort of stands out for anybody or they want to ask about other than those points I just made about it? Because there's many others as well.
I was just wondering why, because the Lofoten Islands are at a higher latitude, so wouldn't you expect to see more all-sky storms and more coronas than lower latitudes?
Yeah, in this case, you know, we don't know. We don't fully know all the definitions of these types. And there's some possibility that because it's that high north, it's not covering the whole sky quite as much. But the other thing I would say, if you just look at the all sky storm category, the only numbers there are like a 1%. And so there's some really low stats there. So maybe they didn't use that category quite as much. Like these categories could have some overlap as well.
Okay, I see.
I'm intrigued by the time frame they chose. I'm just Googling, and it looks like solar cycle 20 ended in March 1976. And these aurora are from 1976 to 1979, so sort of past the end of the solar cycle there.
So more of a solar minimum time, or past the map. I'm not sure which you were saying.
It says solar cycle 20 lasted from October 1964 and ended in 1976, March.
Okay, so it would be kind of a minimum.
Mm-hmm.
Yeah.
So that would be,
Yeah.
since you're at your minimum, you would be getting different kinds of solar activity, as opposed to getting lots of coronal mass ejections and big storms that the storm builds up really fast. You would be getting more of the coronal holes in the high-speed solar wind, and those produce a different type of geomagnetic storm. And so maybe that's part of why the latitude ranges are not, maybe what we expect to see.
Yeah, I agree, Christine.
I have one
Our-
question about the tables
Yeah, sure.
as well. Are these categories that they've chosen, since this paper was published, have there been standardized categories for identifying forms and motion?
No, you could ask any set of space physicists and we would still be arguing about what those types are. Not what they are so much, but how to define the categories. And so, with Aurorasaurus, that was a choice that was made. The main types that we look for were the glow, the discrete arcs, and the patches. The reason we made that choice was because those are definite, largely very distinct types that correspond to different physics. And we wanted a fewer number of types. But if you go somewhere else nowadays that's classifying aurora, for instance, the new Zooniverse project that looks at a whole lot of Themis all-sky camera data called Aurora Zoo, I believe they have some other types as well. And so in this case, yeah, I mean, that's a very good question. I think, suspected glow, if you think about in 1980, a suspected glow is kind of like by eye, whereas nowadays that might be like aurora on camera, that sort of thing, but not by eye. So we could have that category, but again, it's a slightly finer levels than what we use on Aurorasaurus, but it really depends on the purpose as well.
Donna has an interesting comment. Donna, do you want to talk a little bit about what you I think I cut myself off. I said,
sorry. I have noticed the videos and pictures that you see online of the aurora that taken at locations that is always underneath the oval. It does seem to be a completely different perspective than we see. A lot of times it is the same, but very often we see different things coming from that. I guess when the storm is bigger and it reaches down to us, it has become something different than it is on its regular days.
Yeah, and when you're that much further north, it's going to cover more of the sky. And so, yeah, when you're at lower latitudes, it's very interesting. I was kind of struck by this when I came back from Yellowknife and then kind of looking at many of the like Alberta Aurora Chasers type photos, not type, but it's the horizon, but then there's lots of layers in the aurora that you can see from the horizon, but you can't pick them all out. But there's many cases where there's structure and you capture a lot of structure. But I would say if you were in Yellowknife and looking overhead, you tend to get a different type of picture because it's really the perspective, the height.
Yeah, and it's a good point about the activity and the different types of storms, because I remember growing up in northern Minnesota, we would often see the northern lights, and we would see arcs and things like that. But it was very different when I was in graduate school and we went up to Alaska. It's like I had never seen really as much of the color in it before. Where, up at the higher latitudes, we would see more of the coronas, and we would get not just the green, but we would get the pinks and some of the other colors. And so it really is different depending on where you are.
I think this plays really
Yeah,
nicely. Oh, sorry, go ahead.
The color plays into the perspective as well, whether you're able to see that level of color at the like lower altitude, or whether you're really far away, it's harder to see some of those colors. So
I think this plays really nicely into something that Jeremy was telling us about yesterday, is that people's interest in Aurora has a lot to do with the perpetual newness of it, and how it's different in each
yes.
viewing. Liz, we're getting echoes off your speakers again.
Yeah.
Liz,
Okay.
we're getting echoes off your speakers again.
I'm sorry. I was going to suggest we move on. And so maybe you want to read the first paragraph, Laura, and then Hannabella, and then Donna,
Sure.
and I will mute.
Right. The Auroral zone runs parallel with the Lofoten Islands and the Norwegian coast for some distance, so that ships making their way to the North Cape and the Barents Sea are able to observe the frequency of auroral activity more or less directly under the auroral oval, bearing in mind that cloud cover and the bad weather prevents any individual observer from seeing all of the available activity and frequency of the aurora in the region of the auroral oval may be judged from the following table of observations made by ships of the Volunteer Observer Fleet. These vessels contribute their data to the BAA through the good offices of the Meteorological Office. We're moving to the next page, and there is at the top of page 258 another chart.
Do you want to take a cut at interpreting that chart?
Sure, absolutely. So we have the columns read ship or motor vessel, period, number of days observing, geomagnetic latitude range, number of aurora nights observed, and observed rate nights per annum. We have summary reading from August to October 1976, St. Jasper reading from September to October 1977, Miranda, which has 3 rows, reading March through April 1978, December 1978, and February 1979. And it looks like Miranda has just seen a lot of aurora, although at lower, it's a little bit difficult to read this chart because the period of time isn't consistent in terms of the fact that for 2 of them, Miranda is seeing 8 nights of aurora in 1 month in February 1979 and 4 in December, but then 6 in March through April, but I don't know what the breakdown per month is. In the same way that I don't know for Summity what the breakdown of that 9 in August through October is. Did they see 8 in October and 1 in September, or 3 in each month, or something else? So it's a little, I think it's a little challenging on my end to kind of understand what we're talking about, but they're all at more or less a similar latitude range. And
So I think
yeah.
One thing just to say to that, I don't think from this table you can get the absolute rate per month, but I do think you can get a sense of the observed rate, and then these are all different years, and so they were just kind of the observations per year, and that's the last
column, exactly,
which I think is extrapolated to how many nights they would have observed in a yeah, it's extrapolated. So there's a lot of there's uncertainty in that extrapolation for sure.
The range of latitude is maybe important here too, because you have different numbers of observing days, and like the Miranda only had 67 to 68, well, 67 to 69 on the middle one there. But the other ones covered a much broader range of latitudes, and I think it also kind of matters is how many days you spent at a given latitude, since the ranges are different on some of these here.
Mm-hmm.
Yeah, that's right.
I was just looking at Google again, and it looks like they're calling solar cycle 21 as having started in March 1976. So maybe these are the first years of a new solar cycle. Which would be why they chose these particular years.
I don't think they chose them for that reason. I think they chose them because those were like part of the years that were handy at the time they wrote the paper. The recent years. Okay. Well, I think we've lost Hannabella a bit for a very good reason. So maybe Donna, would you like to read the next paragraph?
Sure, if you could tell me. I'm at work and I had an interruption here, and I don't know exactly where we are. Are we just below that chart?
Yes,
the Aurora
we are.
also produces?
Yeah,
exactly.
Okay, sorry. The Aurora also produces a radio event well known to amateur operators. The cause is clouds of ionized particles in the E layer at a height of about 112 kilometers. These can distort or absorb the signal at 435 megahertz from an Oscar artificial satellite traveling behind the Aurora. Better known, they act as scatterers of radio signals and can be used to increase the transmission distance of VHF stations. Measurements show a tendency to a peak of activity at 1900 hours local time, with a minor peak at 1500 hours. The varying intensity of the aurora and porosity of the ion clouds may cause multipath echoes and hence distortion of the received signal. The radio aurora observation comprises the scatter signal. Do you want me to continue?
No, maybe you just want to talk about that paragraph a little bit. That was a pretty dense paragraph. So,
okay.
And we've shifted into radio observations, which is what more of the later part of this article is about. But yeah.
Yeah, well, when we talk about all of the different implications of solar activity and the aurora, this is something that I know is of a lot of interest as to how it affects things, the radio distortions and whatever you call it, that I know when I follow yeah, I'm not sure what I'm trying to say, but yeah, I don't know. I just generally the thought of what they're talking about. I know I have paid minor attention to it following aurora.
Yeah,
activity.
I think the big point is that the radio signals travel further or can get distorted. And so they did vary that a little bit in this paragraph, but yeah, the better known part that the aurora can scatter radio signals and can increase the transmission of certain frequency ranges of those stations. So it's there's also a reference to something called an Oscar artificial satellite, which is a really interesting story because back in the first days of satellites, and even up till maybe today, I'm not sure, there were satellites that could be, I think they were transmitting. I could be wrong on that. And so they're transmitting then through the aurora and being picked up on the ground. It could be the other way around. But they're creating a signal, and then people were observing on the ground with radio signals how that was changing, and they were noting that it was changing when the aurora was changing as well. So there's also reference to an event called the sporadic E layer, which is not the same as the aurora, but an increased layer of a change in the ionization at heights of aurora. And so that has a more complicated connection to aurora. I actually am not going to try to summarize it because I am not too familiar with that. But it makes a reference to that, and that's something that, you know, probably it's not critical to our reading this paper today, but, you know, they make a reference, and you could go back and look at further into that if someone was really interested in that.
I dropped in the chat a link to our the ham radio conference that we took part in a couple months ago. If you're interested in more details about radio and amateur radio operation in Aurora, you can find it there. Let's see. Are we ready for the next person? Maybe Jeremy, would you like to? Oh, sorry, Liz is saying something. What'd you say, Liz?
Yeah, I was just going to say Jim LaBelle's talk is the one there that summarized radio observations in Aurora particularly. So,
thank you. Jeremy, would you like to take the next paragraph?
Yeah, sure. I'll just stop my video to make sure that I get all the bandwidth into audio.
Mm-hmm.
So I'd just like to mention, I really like that that Liz mentioned, you know, don't worry, this is a very dense paragraph in terms of content, and you know, let the audience know that they're not supposed to, if there's a big step or a discontinuity in the content, that you know, don't worry about it. Yes, this is a more complex paragraph, or it shifts subject or something. I think that really helps with the reading and engagement for somebody who doesn't know the subject material quite as well, like myself. So yeah, that's a good comment, and it really helps keep an audience involved in a reading. I'll continue with the next paragraph. Visual aurora tend to show peak rates of occurrence at the equinoxes with a 0 point in summer. I assume they mean the summer and winter equinoxes. I'm not sure what a 0 point is. Due to the brightness of the sky and a secondary minimum in midwinter. On the other hand, radio auroral effects measured in the United Kingdom have shown the spring equinoxial peak and to be about half the strength of the autumnal equinoxial peak, with a 0 point in midsummer and a secondary minimum in midwinter. The writer's observed distribution of the visual activity for the period of 1959 to 78 is as follows. And I'm glad they've got that little table there to help with that paragraph. What I take away from that table is that the percentage of occurrences is, as they say, in the spring and in the fall seem to be 2 peaks, and in midsummer there's a big dip. And around the winter equinox, there's something almost as high as the spring and the fall. Let's see what they have to say about that. With regard to the sunspot cycle, the visual aurora peak with a flare activity followed by a lull and a secondary M region peak of about 3 to 4 years after the primary peak, according to the observer's location. If the solar activity is low, then the secondary peak assumes predominance, as in the last solar cycle of 1973. The radio aurora peaks up to 2 years after the maximum sunspot activity. So it sounds to me like you could really dig into this paragraph with the details of the relation, but they're saying that the radio relationship is to the calendar year, but also to the solar cycle, which is 11 calendar years approximately, if I understand that correctly.
yeah, that's a good summary. There's two, you know, there's the solar cycle time period, and then within 1 year, there's also equinox kind of peaks and differences. I think the main point they're saying is that the visual aurora doesn't peak in exactly the same way as these ham radio or radio aurora signals. And that's something I started reading this paper because I wanted to learn more about that and dig into that more. And I'm not sure if we have anybody on the call here who's more into the radio aurora and what that means. But it does have to do with the way that radio is, you know, bouncing off of the ionosphere, and that's changing density. And aurora affects that, but there are differences as well. So, yeah.
I can continue if nobody else wants to go at the moment.
Why don't we'll keep going around. So, yeah, maybe Christine, do you want to go?
Sorry, I was trying to find my mute button. Are we at it is reported?
Yes.
Okay. It is reported that evening radio aurora are diffuse in form, while morning events are discrete. If a magnetic storm commences at about 1700 or 30 hours local time, this will be followed immediately by a radio aurora. Magnetic storms at other times are not so followed. Morning discrete aurora relate to visual rays and pulsating surfaces. Weak radio auroral sources observed in Britain commence to the northeast in Europe and travel southwestwards. There is then a period of up to 30 minutes of quiet, followed by a strong auroral effect passing from northeast to southwest, 300 to 500 kilometers south of the first track, ending in a complete cessation of activity. The discrete radio aurora could possibly result from scattering clouds of ionized gas, rather akin to an ionosphere up on end. The diffuse radio aurora are probably due to horizontal or near horizontal clouds where the transmission paths from the near and far points of the clouds are of significant different lengths. It does not follow that a radio and a visual event will occur simultaneously, for it is possible to have a radio event without a visual aurora and vice versa. In the period 1977 and 1978, a comparison of observations from both types of observer indicated that there were 205 visual and 194 radio aurora nights, but on only 93 occasions did both visual and radio events occur on the same night. With regard to the number of consecutive nights on which visual or radio aurora events take place, it will be noted from the following table that visual events tend to be more prolonged than radio events. So, and then there is below the table showing the number of consecutive nights and then consecutive visual events and radio events.
What do they mean by consecutive exactly? Oh,
if they mean like the number of nights, like if on you know, how many nights in a row maybe.
Yeah, that is what they mean. And this is another table that could be a plot, or probably would be a plot today in some ways. But, you know, as you go to the right-hand side, there's the chance of having a week of continuous aurora or something like that. And yeah, it's kind of,
It's,
you know,
oh, go on, sorry.
I was just going to say they are drawing the conclusion that the visual events are longer than the radio events, or tend to be more prolonged. But, you know, I think that could, I'm not sure if that's, I'm not fully convinced of that from the table. But that's all I want to say, but go ahead.
The other thing that I was wondering is, what do they mean by a discrete or a diffuse radio aurora? You know, because I know, so this is kind of promoting University of Iowa here, that as University of Iowa where I work builds a lot of radio and plasma wave instruments for satellites, and one of the features that you see in space are waves called chorus, and chorus is related to precipitation. And the name course was invented long before we had satellites, because people with listening to radio signals on the ground would hear sounds like chirping birds. And it does happen to be that in space, the region where you are more likely to see this is on the morning side. And that's what I was wondering, is that what they mean by the diffuse kind of things, just sort of staticky radio signals versus having sort of like hearing these chirps and whistles and things? But I'm kind of curious about what they really mean by that, as it's not quite clear.
Yeah, that's not defined super well, but I think you made a really good point. And I do think of chorus as a discrete type of wave or discrete frequencies. And so in this case, they're doing something that's, you know, kind of you might want to watch out for sometimes, which is they're reusing the same term of diffuse and discrete in comparison to Aurora, which also has those terms defined, and they're not defining either of them precisely enough, because they're probably different things, but using the same word makes you think that they're related. But I don't think that that's what they mean.
This is Jeremy. Could I ask a question about the radio stuff in general? I don't know much about it, but I kind of want to find out more. One thing that strikes me here is with visual aurora, I know that I'm not producing the light, the aurora is, but it's not clear to me necessarily whether this is radio events are classified as the reflectivity or absorption of human signals that are trying to be bounced off of the atmosphere, the ionosphere, or if these are actually sort of a transmission by the aurora that are also being received. So I guess it's just a lack of familiarity with their terminology.
I think it's both, actually. So I think those are both of those types of things happen. What Christine was talking about with the chorus waves, those are generated in space and picked up on the ground. They are ducted through the ionosphere and different things happen. But then there's also scattering and the propagation of radio signals that is more of a remote sensing technique as well. Maybe they will explain this more if we go on a little bit more. Vincent, do you want to go ahead?
Sure. Yeah. Aurorae due to ejection of matter from coronal holes on the sun are usually quiet in activity, may last for several nights, and repeat themselves at 27-day intervals as the sun rotates. They are more often detected in Britain as radio than as visual events. The radio signal is unsteady and tends to peak at 1400 to 1700 and 2100 to 2400 hours local time. Most of the aurorae taking place at the end of a solar sunspot cycle are of this type. Aurorae following solar flares produce steady radio effects, often with visual activity in Britain, as the auroral oval expands through the disturbance of the magnetosphere. Peak times are as above. A similar aurora takes place on the breakup of a solar filament. In both of the above types of radio event, the visual phenomenon appears during lulls in the radio event and after the radio effects have ceased. So basically they're saying that when you have a coronal hole become geoeffective, and the radio effects from the coronal holes are usually quiet in comparison to the solar flares, which I guess would make sense, because when you have a solar flare and then a CME, could possibly be launched with that, those can be more potent than just a coronal hole, at least just my observations over the years. But it also says, let's see, there's more visual activity with the auroras from solar flares, which again makes sense, because if there's larger disturbance, then you're going to get more extent of the auroral oval. It's going to expand more. And then also they say that the visual aurora seems to take place when the radio aurora is not as not as active. So I don't necessarily know what that means, but that's just what they're saying. So
it's something that would be really interesting to investigate if we had the means to do that in a system like Aurorasaurus and the ham radio project as well. If we could collect data in the same system and more consistently, you could dig into that more. Be interesting. I like what he's saying about coronal holes as a nice paragraph there.
yeah, that was good. I like that paragraph.
Yeah. Does anybody have any other questions about that paragraph? All right. I think are we back to me on the rota? I believe so.
Yeah, go ahead.
All right. Another type of radio event takes place when strong solar radio frequency flux is detected, but when magnetic disturbances are absent. The event consists of one or more bursts of activity amounting to about 10 minutes or so. They are rarely accompanied by any visual activity, are most often detected between 1700 and 1900 hours local time, and seldom a late night event. Generally, the auroral oval stays in the north. Strong visuals are known to appear without any radio effects at all when the auroral oval moves south, and there is deep penetration of the atmosphere by incoming particles, enhancing the absorption layer in the lower ionosphere. These events are seldom detected in southern Britain. So it sounds to me like they're saying that the sun does some fancy things and it makes radio aurora mostly between 1700 and 1900 hours local time, not usually at the same time as you see visual aurora. But when visuals appear, the auroral oval tends to be moving south. You're seeing the incoming particles really getting into the atmosphere, and you get that strong visual. So it seems like they're kind of distinguishing radio aurora and visual aurora as two separate phenomena, or related but separate phenomena. Is that correct?
Sorry, I didn't hear your very last question, Laura.
Oh, I said it seems like they're distinguishing radio and visual aurora as almost two related but separate phenomena.
Yeah, I think these two paragraphs are talking about distinct things. I don't think they're related to each other.
Okay.
And the first one, I think, is more of a solar radio burst, which I think is more energetic particles and not something that directly causes aurora, but you are literally able to detect that type of, a different type of space weather than we normally care about with the visual aurora.
Mm-hmm.
And then the second was talking more about what happens when there are large storms, and the fact that storms have different, there's a lot of different things going on, but that might not be as, I don't know, distinct in the radio. There might be new research in that way. The ham radio group might have more to say about that as well.
And the ham radio group that we're talking about for people listening online is Ham Radio Science Citizen Investigation, or HAMSCI, who are an organization, and you can visit their website at hamsci.org. Thank you. Does anybody else have questions about that? I would love to see an animation distinguishing the two. I think that would be really helpful to have a visual.
So my question was, I guess the only thing that I was a little bit confused of was why they use solar radio frequency flux. That just like didn't make sense to me.
Yeah, what is a solar radio frequency?
Yeah, I was really confused because, you know, I understand that solar flares and then particle radiation storms can produce, certain delayer absorption in the ionosphere and stuff like that. But the solar radio frequency flux, I was trying to I didn't know if that's what they were talking about. Or maybe, maybe they didn't even know what those two terms were at the time that they were writing the paper, but.
So I put another link in here. There is a type of radio emission called a solar radio burst. There's like type 1, 2, and 3, and they produce, it's basically when you have like a shock wave associated with like a CME or a solar flare, you get particles that are up front of that, accelerated at front of the shock wave, and they can produce this radio signal that swoops down in frequency as the disturbance propagates out. And the example that I put in there was recorded by Cassini, but you can also see them on spacecraft that are near Earth. And maybe that's part of what they were getting at in there, but were a little bit unclear about the physics, where they talk about aurora following solar flares, because when you have you see the solar flare first, obviously, and then the particles get to you, and then you would have whatever solar wind disturbance that accompanied the flare would give you the aurora after that. And so maybe that's part of what they're getting at here, but I'm not entirely sure myself.
I think it is. I agree with you, Christine. I think they just used the term flux. Maybe that was the term at the time instead of bursts or something like that. Yeah, okay, let's keep going.
We have about 8 minutes left.
Is Donna next? I think so.
Okay, are we at exact details?
Yes, ma'am.
Exact details as to what causes a particular radio aurora are seldom clear, but observations made by J. Brannigan at Saline, Fife, between 1977 September and 1979 September fell approximately into the following categories. So the table. The missing 7% could be a possible result of proton precipitation of the form described by Aether and Mende. It is not to be noted that solar flares tend not to produce radio aurorae in June and July in Scotland. Elementary texts on radio wave propagation give the impression that waves are reflected from ionospheric plasmas such as the E layer. Reflection can only take place at a mirror surface, and the turning of the signal is more like a scattering effect, with some ducting of signals along the ionospheric layers. This is probable in the auroral scatter of signals, as Brannigan has deduced by measuring the azimuth and the altitude both of his own aerial array and those of other VHF stations with which he was in contact by means of auroral signal propagation, noting at the same time what stations could or could not be contacted by this method. The plots of Brannigan's radio aurora plasmas appear to be parallel the locations of the expanding visual auroral oval, according to the degree of magnetic disturbance. The paths of the transmitted and returned signals between transmitters and receiver via the auroral activity follow a scatter rather than reflected path mode.
You get the dense paragraphs, Donna. You win.
Yeah. I win, and I'm the most uneducated one in the group.
Donna, I'm new. I'm really new. You're good.
Well, I don't know if it'll make you feel better, but I'm on Wikipedia for ionosphere D, E, and F layer, right now. While you were reading that, I was like, oh God, I'm going to butcher this. But basically, the short story is that those D, E, and F, they go up in altitude, and they're distinct bumps, enhancements in the density of the ionosphere at different heights. And they change day to night because you get different amounts of plasma day to night. And so what I don't know, as I was like frantically scanning that little Wikipedia page, was the origin of those terms, because I vaguely recall they do actually have to do with radio bouncing of the signals, and something to do with that, possibly with the Navy way back when, but I'm probably misremembering that. Anybody else want to say more about that?
I don't have more about that, but I'm wondering what ducting is.
Oh, ducting is the bane of my existence. So, so the sources of these radio signals and also various other plasma waves all are in space. And you can observe them. Obviously, the people who wrote this paper were you know, it sounds like some of them were like ham radio operators, sounds possibly over at radio frequencies. And there's also a lot of ground magnetometer stations that are monitoring things, and you can see these sort of radio signals in there, or not radio signals, but like magnetic field oscillations and other signals. And the way that they get down, it's hard to tell where they come from exactly sometimes, because the way that they get down to the ground is not like just a straight shot. That you know, as Liz kind of was talking about the different layers of the ionosphere, is that these different layers and where they are situated at any given time affect how radio waves propagate on the Earth. You know, so if you're listening to the radio, depending on what is happening up there, you can pick up you know, signals from different locations transmitted from one location on the ground and in another location, and that will change depending on what the ionosphere is doing. And the same thing happens if a signal's up in space and is propagating down to the ground. The properties of the ionosphere affect where it goes, so it won't just travel straight from the source down to the ground. It will travel down in the ionosphere. It may propagate around the Earth in a strange way before it gets down to the ground. And it's something that people are still sort of struggling to understand, other than we know that it happens, and it depends on basically the different layers in the ionosphere and where they are situated depending on solar and geomagnetic activity. I hope that made sense.
It sounded, it helped me.
Thank you.
Yeah, and I'm also looking at Jeremy's comment about the paper and really space physics in general. There's a wide range of observers and diverse methods. And, you know, there are all kinds of correlated, like basically you can observe the magnetic field and the waves in variations in the magnetic field. There can be waves there. You can observe electric field signals and waves there, radio waves and the change in the propagation. Of course, the visual aurora. The visual aurora is like the visual end result of all of the plasma physics and the charged particles and the electricity and magnetism that's going on as well. And so that's why we put all of these observations together. But that's also what makes it tricky to see how all of those things are correlated. Yeah.
Thanks, Liz.
Yeah.
So the last couple of paragraphs are sort of the credits. Does anybody want to read through those? There are three paragraphs where he thanks a whole bunch of interesting people.
I can do it.
All right, thanks, Vince.
Much work still remains to be done in the correlation of visual and radio auroral activity in the above summary, which is mainly based on the work of the United Kingdom visual and radio observers, may well have to be updated in the future. The writer wishes to express his grateful thanks the many observers of visual aurorae in the BAA, the Volunteer Observer Fleet, the Norwegian Astronomical Society, and others who, together with British radio operators, are contributing data for auroral studies. In particular, special thanks are due to John Brannigan, Saline Fife, who for 2 years has spent so much time observing and analyzing radio aurorae, answering the writer's numerous questions, and providing so much of the radio data reported in this paper. Elementary details of the visible aurora and the simple methods of making useful visual observations are given in the Aurora Group Observer's Notes, which may be requested from the writer by sending a stamped, addressed envelope to him for return of a copy. There is currently no elementary textbook devoted solely to the aurora, but useful background data are given by Newton, Livesey, and Radcliffe. Radio enthusiasts may refer to works by Evans and Jessup and ITT. Scientifically oriented students with a historical interest in the aurora may wish to consult Herring, and for a general technical picture of the geophysics will find Beer informative. For advanced technical reviews of the whole geophysical background of the aurora, readers could do well to follow the writings of Professor Shin-Ichi Akasofu.
Yes, Shin-Ichi Akasofu. That's a very
there we
famous
go.
name in physics. So yes, it's all good. I like that. The part that sticks out to me there is no elementary textbook is still devoted solely to aurora. So that's part of the reason why it's why we're here. And this is useful. Yeah.
Jeremy has a suggestion related to that. Jeremy, would you like to talk about that a little bit?
Oh, sure. Yeah. That last line really stuck out to me too. There's currently no elementary textbook. Has that changed in the last 40 years or 30 years since this? Well, 40 years since this was written.
No, I don't think so. Space physics still kind of largely starts at the graduate school level because of the level of physics. And so I do think, and then there are some undergraduate texts, Christine might know better, but there aren't any that are devoted to aurora. Melanie Windrich's book, I think, while not a textbook, is definitely the best that we have that covers a lot of auroral physics right now. Yeah.
And I'm just going to jump in on that really quickly for people listening to this on YouTube. We did a Q&A with Melanie that's also available on our YouTube channel, and I will list that in the description.
Christine, do you have any thoughts on that?
I was like, what, sorry, I missed the other thing because I was trying to find an Akasofa article. So what did you say? Could you repeat that again?
Just if you have any thoughts on undergrad level textbooks on aurora. Yeah.
Yeah, I don't know. There was a book many years ago by Neil Davis, who was a faculty member at the University of Alaska, called the Aurora Watcher's Handbook. And that might be the closest thing to...
That's also very good. Yeah, that's 20 years old at this point, but it's very good.
Yeah, I mean, I haven't followed a lot of that recently. I was just gonna say, if you're looking for another older article, I think I have the right one. I'm not sure. Akasofu had an article in EOS, which is the American Geophysical Union's newsletter type publication, and I'm not sure if I quite have the right link that I just pasted in there, but he also, I remember when I was a student, that some of those articles that he wrote in EOS, since they were intended more for a more general audience, not just space plasma physicists, but like sort of across all of the disciplines that are covered in American Geophysical Union membership, that they were written in more of a general thing, but that was from the 1990s. And so those are also, like you said, 20 years old. So yeah, I have no idea. Most of them are written are written sort of upper division undergraduate level or graduate level plasma physics. So
it's a real challenge. It's something I'm interested in, and it has become more and more apparent to me that there's a gap there for sure. Any final thoughts?
We did have a request from Sarah, who was unable to be with us today, that we do this again with another article soon. She really enjoyed it and hopes that we continue.
Okay, we'll take suggestions for that. I'm sure we can find others.
And then Donna was wondering about the Aurora Share campaign, which we have just decided we're going to extend for another week. We have had a number of observations. The last time I checked, I think it was about 40. And it's been really cool to see so many people coming together to put together this list of observations from 2019. It's really neat, particularly with so many folks submitting photos, to get to see what they got to see last year. We had a neat thing where somebody submitted a photo that was taken a year ago yesterday, so it was kind of an interesting continuity there. But we will be continuing that for another week, so please log on to Aurorasaurus and submit any observations from 2019 and early 2020. And just to be clear, you're always welcome to backdate observations if you have observations you didn't get a chance to submit in real time. So thank you all so much for being here today. We really appreciate your sitting down with us to look over this article. I will be posting this on YouTube, and we will all have access to seeing it. Liz, do you have any other comments? All right. Well, thank you all so much, and we will see you next time. Have a great one.
thanks, you too.
Yeah.
Thanks.